let's just review what we talked about last time. Last time we talked about atoms. So the structure of the atoms, they're going to have a proton, have a neutrons, and electrons. And also for atom itself, the proton number should be equal to the number of electrons, right? Those two are same, which means those are neutral. The whole atom is neutral. But if it's not neutral, then we're going to have ions. We're going to have ions. So if the proton larger than the electron, so remember, proton has a positive charge, electron has negative. Number of this proton, which means, you see, we have 3 positive or 5 positive, then we have 4 or 3 negative. Then we have 2 net positive for the overall particles. Then they give the particles and a charge. So the charge, the atom, is not called the atom, it's called the ion. Okay, charged atom is called ion. So if the proton larger than electron, then it's called the cation. If the proton smaller than number of electrons, then this is anion. Okay, so the cation, anion, this is the difference. And then we also talk about the isotope, right? Like carbon 12, carbon 13, the carbon 14. So those are isotopes, but each of this one is represent one of the atom. Okay, each of those are all atom. So you can think about this is atom 1, this is atom 2, and this is atom 3. Okay, so there's 3 of kind of atoms is a group, and this group is what we call the isotope. Okay, remember, so that's why isotope is not a special, it's a special name for a group of atoms. Okay, so each of those are all atoms, but they're having a same category. It's called isotope because they belong to the same elements, but they are different, right? So each of those atoms are different, but they belong to the same elements. So we call this group of atoms isotope. Okay, we call the group of those atoms isotope. And I also talk about, please recognize the difference between this. Okay, so if we just write C or C12, what is difference between those two? Very, very important. So if you didn't recognize, let's see. Okay, proton, neutron, and electrons. Okay, so answer my question. Do we know what is the proton number for those 3? What's the proton number? 6. Okay, because the carbon has 6. Do we know the electrons number for each of the 3? 6, because I didn't write the charge, so that's neutral, and the 6. Do we know the neutron numbers for the 3? Not all of them, right? Not all of them. We know carbon 12, since this is a mass number, right? So mass number is equal to proton plus neutron. You already have the proton, so you know the neutron, right? So this is 6, and this is 7. But do you know this? You don't know. You don't know, right? Because I didn't write anything on this. So that is why this is the difference between those two. Okay, yeah. So that's why we call each of this is an atom. It's one kind of atom, or we call, yeah, this is one kind of atom, because as long as you know how many number of proton, how many number of neutron, how many number of electrons in the particle, and generally you can identify what kind of atom it is. But this is just to give you a general idea what kind of element it is. So that's why this is a general elements. Just the general elements. The carbon C is just the general elements. It didn't show what kind of the atom it is because we don't know what is a neutron. There could be a neutron, the neutron number could be 6, could be 7, or could be even 8, okay, or more. And then they are giving you different atoms, but this one didn't specify. So we call this just elements, okay, a bigger category than a specific atom. Are you clear? Okay, yeah. So that is the why. If you see the mass number shows over there, then you know this is a specific atom, okay? But if you don't have the mass number, that's just a general elements. Are you clear? Okay. Okay, so this is what we talk about in general, right? And also talk about the practice in the page 17. Have you? If you're given a chance to finish the rest of them, you need to finish that, but not in the class, okay? And by the way, to doing the practice in the chemistry, you do need to spend the time after the class, okay? If you just spend the time in the class for chemistry study, that's not enough, okay? You do need to do the practice after the class, okay? So that's why I give you the study guide. The study guide is helping you to do the practice. Very important. Okay, yeah, very important. Yeah, the more the better, and you will see the quite difference. You will be excel in the exam. Okay, you will be excel in the exam. So very important. All right, so here we talk about the isotope, atoms, cation, anions, atoms, how to figure out those numbers. Then the next part, we're going to talk about one of another concept is called the average atomic mass. Okay, so remember when we talk about this 39.0983. So this is what we call the average atomic mass. Why this is average atomic mass? Or another examples is the carbon. I'm going to using the carbon as an example. This is a 12.0108. Okay, yeah. So carbon, and those are also called the average atomic mass. Why this is average? Okay, that's because so this is the general mass for elements. Remember, this is a general mass for carbon elements. Remember, we talk about carbon elements could have the different atoms, right? Could have a carbon 12, carbon 13, carbon 14. So this is the general average for all kind of the carbon elements, carbon atoms. Okay, yeah. So for example, we talk about last time we talked about carbon 12, carbon 13, and carbon 14. And in general, we talk about those are mass number. Why we call this is the mass number? Again, I talk about why this is called a mass number. Is related to the mass, right? Why this is related to the mass? This is talking about how many protons plus neutrons. Why one proton is just equal to one of the mass? It's about the same weight as an AMU. Okay, so there's a unit is called the AMU. Okay, and the AMU is called the atomic mass unit. Okay, The reason we're using this is because, okay, you can, I will find some of the example for you, okay? So average AMU. Okay, what happened? So AMU to gram. Yeah, so what? Completely so generally this is the AMU. You see 1.66 times 10 to the negative 24. So this is the AMU. Okay, one AMU is close to 1.66 times 10 to the negative 24 gram. Okay, so AMU generally is a mass unit. Okay, but this mass unit is really, really small. You see 10 to the negative 24. Okay, yeah, so it's really, really small, but we're still using this number unit because this unit is talking about the mass of the atom. Okay, yeah, and we talk about one proton, the mass generally is close to AMU. Okay, and one neutron, the mass also very close to AMU, although it's not exactly the same, but very close. Okay, yeah. So that's why if you have a one proton, and generally you know the mass is 1 AMU. You have 10 protons, you know the mass is 10 AMU, right? If you have a 20 mass number, which means a 20 proton plus neutron, then you know this is about like a 20 AMU. Are you with me? Okay, yeah. So that is why the mass number generally is talking about the mass for the each of the atoms. And again, I need to emphasize that this mass number is not exactly the mass of the atom. Because you see, this is a close, it's not exactly the same. Okay, yeah. So some of the question will just give you the mass of each of the isotope atoms, okay? But some of, if it's not giving, then you can just assume the carbon-12 is about 12 AMU. And carbon-13 is about 13 AMU. And carbon-14 is about 14 AMU. You know this, right? Okay, yeah. So you see, each of the atoms, they know the mass. They have the mass shows up there. But why, when we talk about this, it has a fractions over there. Okay. Then this is what we talk about the weighted average. Okay, yeah. Normally when we do the average, we have like a 1 plus another divided by 2, right? So this is the average we talk about. Or if you have three things, you add those three and divide by 3, right? So in this case, you weigh each of those value equally. Okay, for example, if you have the average A plus B divided by 2, generally you weigh the A and the B 50-50%. You both equally the same. Okay, so in general, you can rewrite this as just A times 1/2 plus B times 1/2. Okay, so generally those are value is the same thing. Okay, so this is just a 50% times A plus 50% times B. So your way the A and B is the same. Okay, yeah, equally. So that is why this is how we normally do the average. But in the carbon or elements is different because those three, the carbon-13 or carbon-12, they present in the different weight. Okay, in the different percentage. Okay, here before we do the calculation, I need to emphasize Carbon 12, carbon 13, those are is called a standard isotope or stable isotope. Sorry, stable isotope, which means the stable isotope means this isotope is not going to change. Okay, it's not going to change. So once it's carbon 12, they will going to be carbon 12 forever. Okay, but the carbon 14 is different. Carbon 14 is a radioactive isotope. Carbon 14 is a radioactive isotope. In another word, this isotope is changing, okay, or is a disappeared from carbon 14. It probably will change to the nitrogen, okay. So in a short period of time. So that's why when we calculate the average atomic mass, we never count the radioactive isotope. We only count for the stable isotope for the average atomic mass. Okay, so let's continue talking about, okay, how we talk about carbon 12, carbon 13, and when the carbon 12, carbon 13, they present in the word, they are not equally present. In another word, we do not have 50% of the carbon 12 plus 50% of the carbon 13. But in the real world, it's about we have 99% of carbon 12 and only 1% of the carbon 13. So this is roughly an idea. In another word, if we have 100 atoms of carbon, if we have 100 atoms of carbon, we probably have 99 the carbon 12. Only just one atom is carbon 13, right? So that's why in this case, we're not going to weigh the mass of the carbon 12, carbon 13 equally, because those are not equal. Most of the carbon 12 dominate in the whole world, right? So you cannot just add the mass of carbon 13 plus mass of the carbon 12 divided by 2. This doesn't make sense because most of we have carbon 12, okay? So that is why we're doing another kind of the average. It's called a weighted average, okay? So the easy way to do the weighted average is you're using carbon 12, the mass, multiply the percentage of this, 99% of this, and this is what we call the abundance. So 99% is the abundance of the carbon 12 in the whole carbon elements, okay? And then you're going to have one of the value. And the carbon 13, that's a mass, also time 1%. And this is the percentage or abundance of the carbon 13 in the whole world. And this is also what we call the abundance. And you got one of the value, okay? And then once you got the two values, you add those two together, then the summary of those two will be the average atomic mass. Okay, the summary of those will be called the average atomic mass. Okay, so let's just roughly do the calculation. We already assume the mass 12, carbon 12, the mass is 12 AMU. Carbon 13, that's a 13 AMU. Okay, so in this case, use a 12 AMU times 99%. 12 times 0.99. 99% is 99 divided by 100. Okay, so there's no percent sign in your calculator, but you can do is just 99 divided by 100. This is the same thing. Okay, yeah. So 12 times 0.99. That's the value for the first one, 11.88. Okay, and this is AMU. For the 13 time point 0.01. This is 1 divided by 100. You got 0.13. 0.13 AMU. And then you add those two together. 0.13 plus 11.99. Then you got one number, 12.12. Okay, 12.12. Okay, did I got it right? 12 times 0.99. Oh yeah, 11.88. Sorry. This is 8 and this 8. Then 0.13. We got 12.01. Okay. That's 12. Wait. AMU. Are you clear? So that is why we got the average atomics for carbon is 12.01. Okay, so this guy shows over here is more accurate. Either it's because the percentage they write is more accurate, or the average the atomic mass for each of the carbons isotope is more accurate. So they got more accurate results. Are you clear? Okay, so this is how we do the average atomic mass. So we have the mass for each of the isotopes, and we time the percentage of that. We got a result, and each of them you time the mass time percentage, then you add up everything. Then that's going to be the average atomic mass. Okay, yeah. So let's do some of the practice. Okay. Study guide, page 19. Okay, study guide, page 19. And also, I sent an email to everyone about some videos about the average atomic mass and the relationship between the molecular compound and the ionic compound. Have you already watched that? Okay, yeah. So this is kind of like a review. Okay, so for the first one, again, the first one shows over here. This one, say we have a rubidium has two common isotope, rubidium 85, rubidium 87. If the abundance for each of this is already shows there and says what is the average atomic mass of rubidium. Well, in general, this question didn't show what exactly the mass for rubidium 85 and what is the mass for the rubidium 87. So in this case, we can just assume the mass number is the mass of those isotopes, right? Yeah. So now the rubidium 85 has 85 AMU, and the abundance for the rubidium 85 is 72.2%. Okay. Yeah. Then rubidium 87 AMU time the abundance of it is 27.8%. Now, what we need to do is just figure out what is the percentage for each of them, right? 85 AMU time 72.2%. 72.2 divided by 100. 61.37 AMU. $87 times 27.8 divided by 100. 24.156 AMU. Okay, so now you add those two numbers, add those number and those number together. That's will give you the 61.37. and got a 85.556. Okay, 85.556. But in general, you need to keep two decimals because the final is addition, right? The addition you keep at least the decimal point. So this is, so that's why that's about like a 85.56 AMU in this case. 85.56 AMU. Are you clear? Okay, so this is how you do the average atomic mass. And I would like to talk about one more. Okay, so you can think about the question number 4. Okay, this one, they said that this is a 4 isotopes of lead, and they have the structure of there. Okay, they telling us 4 isotopes A, B, C, D, and they shows the protons, neutrons, and percent abundance for each of this. Okay, how do we start it? Remember, for the isotope average atomic mass, you need to know the mass number or mass for each of the isotopes, and then you multiply the abundance. Do we have the mass? Shows up here, mass for each of the atoms. They only telling us the proton and the neutrons. Then how do we start? Add them together, right? Add them together, you got the mass number. So the mass number is close to what they have. What's the mass of each of the atom? That makes sense, right? Yeah. So you add them together. The first one, so for the A, and there's 82 plus 120. That's 204. So 204 AMU. Then you time 1.37%. Okay. For B, that's 82 plus 124. So we have 206 AMU, and you time 26.26%. For C, we have 82 plus 125. That means we have a 207 AMU time 20.82%. And D, 82 plus 126, so that's a 208 AMU, and you time 51.55%. Okay, so once you got each of this, then you add them together. That's it. Okay, yeah. So 204 times 1.37 divided by 100, 2.794. 2.7, wait. 7948. $206 times 26.26 divided by 100. 54.0956. 54. 54.0956 AMU. Then next one, 207 times 20.882 divided by 100. 43.09474. 09474. 43.090974. Next one is 208 times 51.55 divided by 100. Got a 107.224. AMU. Okay, then you add them together. So 2.7948 plus 54.0956 plus 43.0974 plus 107.224. And we got 207.221. 207.21 AMU. You see, so that is why we got this number. That makes sense? Okay, yeah. This is how we do the average atomic mass, generally the same. And I just need to want your emphasize this. If this question do not give you the mass for each of the atoms, then you can using the mass number. But if the question do telling you the mass of each of the atom, then just using the mass of each of the atom. You don't have to using the mass number. Again, the reason we're using the mass number because the question didn't show us the exactly mass for each of the atom. That makes sense, right? Okay, yeah. All right, so this is the average atomic mass. Okay, then let's take a little bit break. Okay, so 3 minutes. Okay, so let's come back. Okay, the next part we're going to talk about a little bit about the periodic table. Okay, how we set up the periodic table. And here also the time, you can start to draw something on your periodic table, okay? And just let you know, you can draw whatever you want. And you can also bring that for your exam, unit exam. Not for the final, but for the other exam, you can take it, okay? So the periodic table is generally is something like that. And there's another two rows of the periodic table shows over there, right? Yeah. So it's a general like this, okay? And they are separated into several parts, okay? Yeah. This one, this parts, and also this parts, okay? We give it a name, okay? So if we have this slash this group, this parts we give its name. This is called the A group. Or people call this is a main group, okay? Either it's called the A group or main group, okay? Yeah, both are right. Either A group or main group. And if you're looking at over here, this group has a 8 columns. The main group, 1, 2, 3, 4, 5, 6, 7, 8. So that's a 1, 2, 3, 4, 5, 6, 7, 8. Okay, some of those periodic table they shows like 18, but just let you know, the 18 is talking about the total columns from here to here, including the stuff in the middle. Okay, yeah. But if you're only talking about a main group or A group, there are only 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah. So when we talk about each of the column, the first one, this is 1A group. This is 1A, and then 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Okay, and those are A group is the most common elements. Okay, and also those are the elements we focus in this chemistry class. Okay, in this chemistry class. For the rest of others, including these parts, and this is what we call the B group, or people call it as a transition metal. Okay, B group or transition metal. Okay, so this is the B group and the transition metal. This is what they talk about over here. Okay, B group and the transition metal. So transition B group is not focused on. We only pick some of the elements you probably need to remember. For example, iron. You're gonna know what is the iron. Okay, copper, zinc. Those are all in the transition metals, silver and gold. Okay, yeah. So those are the very common that we probably gonna use. And also, I think vanadium, chromium, those are common, okay, ions in the transition metal that we are going to talk about. And just let you know the why we have additional shows in the bottom parts. And this parts actually should be stuck over there. Okay. In another word, the shape of the periodic table shouldn't like this. The periodic table should be something like that. This is and again, those are A, and this is A, and this is a B, which is shows over here, and this is over here. Okay, yeah. So suppose the periodic table is a stack like this. Okay, but usually we don't have that long of the page, right? Yeah, if you write like this, generally you're gonna have a much smaller size of those each of the elements. So that's why the people just moving those parts over there. That's the reason. Okay, yeah. But the real periodic table should looks like this. Okay, should look like this. Okay, so this is what we talk about A group and a B group. Okay, yeah. And then let's talk about the some of the important columns. But most of the column we're talking about is A group. Okay, so first let's talk about the 1A group. So what is the 1A group? The 1A group is called alkaline metal. Alkaline metal. So that's including lithium, sodium, potassium, rubidium, silicium, okay, and also francium. But francium is radioisotope. Okay, this is a this is radioactive elements. So generally, we're not talking about that here. But most of the cases, we're talking about the first 5. Okay, those are called the alkaline metal. But the alkaline metal, although you see the hydrogen is still also in the 1A group. See, hydrogen is also in the 1A group, but hydrogen is not a metal; it's a non-metal. So when we talk about a 1A group, we only talk about those 4, those 5. Okay, yeah, from lithium, sodium, potassium, rubidium, and silicium. Okay, and those are is a group. Okay, this is a group. In another word, if we talk about the columns, in a column, then in the periodic table, that means a group. Okay, we have 8 groups in the main groups of there. Okay, so the first one has a name is called the alkaline metal. Okay, alkaline metal. So the reason we group them together, in general, it has a similar. Those guys has a similar physical and chemical properties. Similar chemical and physical properties. For example, the 1A group, those guys are very soft. You can just use a knife to cut this, just like a cut as like tofu. You know what is tofu? They just cut, very easy to cut. Okay, yeah, and those guys are very reactive with water. Okay, water is not that reactive with the other stuff, but 1A group, once you toss the pure metals in there, they're going to harshly react with water. I can show you some of the videos. Okay, yeah. What happened? Again. What? My computer has some issues. Yeah, always. Sometimes just doesn't work. Yeah, sometimes it just doesn't work. I have no idea why. Anyone knows the technique? I mean, I have no idea. I mean, why we. Okay, so now this is better. Okay, so water was. So the alkaline metals with the water, and you can looking at. Wait. Can you hear me?
In air, the elements quickly become coated with compounds that form on the metal surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Okay, so this is what happens for those alkaline metals. It's very reactive with water and oxygen. Okay, yeah, and also you can see this is also normal. If you go down those in the group, then it's more reactive. Okay, generally it's more true for all of those. Okay, yeah. So this is talking about the alkaline. And the next one is a 2A group. 2A group is called the alkaline earth metal. Alkaline. Alkaline earth metal is also very active. It's a metal, but it's relatively less active than the 1A group. Okay, so that's gonna be including everything shows up there. Beryllium, magnesium, calcium, strontium, and barium. Okay, the last one is radioactive, so we're not talking about that. Okay, so again, the reason we group them together is because they are going to have a similar chemical and physical properties. Okay, and the last one, the next, we're not going to talk about 3A. Not talk about 3A, 4, 5, 6, and then we're talking about 7A and 8A. Okay, 7A has another name. It's called a halogen. It's a halogen. Okay, and 7A, those are all diatomic elements. I already talked about what is a diatomic, right? It's an elements, but made by same two same atoms together as a molecule. Okay, so those are diatomic elements. Okay, so this guy like fluorine gases, chlorine gases, and then I have a beryllium. Beryllium is a liquid in the room temperature, and the iodine is a solid in the room temperature. So we have those halogens. Halogen, again, those are grouped together as they have a similar physical property, which means those are all diatomic, and also they have a similar chemical properties. Like this guy is very easy, very reactive with 1A group. Okay, so one of the example is just a sodium chloride, right? Sodium chloride, very easy to react with. Okay, okay. Then the last one is called a 8A group. 8A group is called a noble gas. Noble gas. The reason it's called a noble gas, and those guy is neon. Including helium, neon, argon, krypton, xenon, and also the radon. Okay, so those are, again, radon is radioactive, but the rest of others are not. Those guys are gases, And also, this is what we call the monoatomic gas. Mono, that means in chemistry is a prefix. It's talk about one. Okay, monoatomic is just one atom gases. So those guys are all just one atom, but those are all gases. Doesn't matter which one. Even the radon, very, very heavy, shows up there. But it's still a gas, okay? Still a gas. Have you heard of radon before? When your parents buy the gas or buy a house, they need to do the radon test, especially in Kansas, okay? Because in Kansas, we have a basement, okay? As long as you have a basement, you need to test the radon, okay? Because radon is radioactive and very heavy, and usually the radon is going to be accumulate in the basement, okay? And if you're going to have a radon numbers is high, which means and then you intake that into your body, that's heavy gases. It's not that easy to come out, okay? When you do the respiration, okay? So it will damage your lung. So this is why the people, you need to measure the radon test, do the radon test before you buy the house, okay? Because you never know whether this house has the issue or not, okay? Yeah, yeah. So this is one of the radon, okay? Yeah. So those are called noble gas. The reason it's called a noble gas is because those are very, very inactive. Okay, noble, very, very. You see, what does the noble mean? I know the noble is a title, right? Or that means it's very high it's not going to react with any others. Okay, so it's really, really inactive. Inactive, we call this, we give it another word, it's called inert. Very, very inert. Inert, I think it's spelled like that, or there's two N's. Very, very inert, which means very inactive. Okay, so those are noble gas. Okay, now we talk about the periodic table in the groups. And in general, they group them together with the chemical properties, similar chemical property and physical properties. And now we're talking about the period or the rows. Rows in the periodic table is called a period. It's called a period. And the period, we totally has a 7 period. Although the first period only have 2 elements, hydrogen and helium, but this is still 1 period. And then it's go down, totally we have 7. 1, 2, 3, 4, 5, 6, 7. Okay, so totally we have a 7 period. And if you're looking at the period for the trans, then you will see on the right side, on the left side is a more metallic. On the right side is a more non-metallic. Okay, metallic means it's more like a metal. Okay, non-metallic is more like a non-metal. Okay, and there's something in between. Something in between shows this is called a metalloid. Okay, it's called a metalloid. It's called a metalloid. Okay, so metalloid is those chemicals, is elements that's similar to metal and also similar to the non-metal. Is in the transition. Okay, yeah. So now you can mark in your elements periodic table. What are those metalloids? We only have several the metalloids that you're going to remember. The first one is a silicon. Okay, the silicon and the germanium and the arsenic and the antimony. The next one is a tellurine, and then it's polonium and actinium. Okay, but those two we're not talking about because those two are radioactive. Okay, yeah. So generally, it's the silicon, germanium, arsenic, antimony, and the tellurine. Those are what we call the metalloid, which means their property is more, sometimes behave like a metal, sometimes behave like a non-metal. Okay, the reason we call it behave like a metal, the major property for behave like a metal is they can transfer, they can let the electricity go, right? Yeah. So this is silicon can also let the electricity go when we apply very high pressure, yeah, high voltage, high potential voltage, then the electricity will go through. Okay, but most of the cases is not. So the behavior is in between between metal and non-metal. So that's why this is what we call the semiconductor, right? And that's why when you're making the chips in your electronic device, we're using this. Okay, yeah, because they can let the electron go and then sometimes don't let the electron go. So in this case, we can control go or not go. Okay, and then we can count 1 and 0 because when you're talking about is a binary things. So go and not go, and then you can take for digital purpose. Okay. Anyway, so this is a metal, metalloid, and non-metals. Okay, yeah. Everything on the left side is a metal. Everything on the right side of the metalloid is a non-metal. Okay, so if you look at the periodic table, most of the case are metals, right? Most of those are metals, and very countable. non-metals shows up there, right? And also metal, if the metal has an ion, become ion, they always become a cation, which means a positive charge. Okay. If the metal become ion, they always become a cation. Non-metal, most of cases is become a anion, which has a negative charge, but not sure for the metalloid. The metalloid sometimes can be a positive, sometimes can be negative, so not sure. So that's why those are the difference between metal, non-metal, and the metalloid. Are you clear? And if you're looking at the trends, if the elements are more close to the left side, it's more like metal. It's more close to the right side, it's more like a non-metals. Okay, yeah. So this is also the trends for the periods in the periodic table. Are you clear? Okay. And this is give you the rough idea about the periodic table. We will talk about the periodic table later. Okay, yeah. But here is just to give you some ideas. The next parts, we're going to talk about the compound. So generally, we reviewed everything about the elements or atoms. So now we talk about the compound. The compounds is including two parts. One is called the ionic compound. The other called molecular compound. Ionic compound, the reason is called ionic is because they are formed by ionic bond. In another word, the molecular compound is formed by, it's not called a molecular bond, it's called a covalent bond. Okay. So let's first let's just introduce what is the ionic bond, what is a covalent bond. Okay, we will talk about in the unit 4 in detail, but here I'm just going to introduce the ionic bond. Means they're bonding together by the charge, right? For example, if we have sodium ions and with chloride ions, so those are ions. Sodium, that's a cation. Chloride ion, this is an anion. So the positive charge and a negative charge. So the positive negative charge, they're going to have attraction, right? This is called the ionic attraction. So those attraction, the bond is just based on the attraction between positive charge and the negative charge, and they're making an ionic bond. Okay, yeah. So this is in general idea. The ionic bond is making between the positive charge and the negative charge. The bond actually you can call this is a force attraction. It just attract them together. Okay, the positive charge and negative charge attract together, making an ionic bond. Okay, making an ionic bond. So those are generally is ionic attraction. This is how we form the ionic bond. Okay, this is how we form the ionic bond. But the molecular compound is not doing this way. Molecular compounds, they do not have an ion. Okay, if they have an ion, then this is called ionic bond. Okay, so they do not have a bond. So we have several of the atoms, group them together, but they are grouped together not with a bond. They group together in another way. Is they're sharing the electrons between each others. Okay, so they're sharing things between each other. sharing electrons between each others. So this bond is not as strong as the ionic attractions. Ionic attraction is more stronger than the covalent bonds. Okay, than the bonds between molecular compounds. They are sharing electrons. You don't have to understand what does that mean, sharing the electrons. We will talk about this in detail in the unit 4. But I'm just saying here that the ionic bond and the molecular bond are completely different two things. Okay, those are two different. So that's why we have those two kind. And later when we talk about naming, those are two different ways to name those compounds. Okay, yeah. So that's why I'm showing off here. Okay. So any questions? Okay. So that's why when we write the ionic compound and the molecular compound is also a little different. Okay, yeah. When we write the formulas is a little bit different because first we're going to talk about the ionic compound. So majorly the ionic compound is made by metal plus non-metal. So the first elements must be metal, okay, or must be a metal ion or some of the what we call the polyatomic ion. We will talk about this later, okay, but have to be ion. This is the first one have to be a cation. The next one have to be a anion. And this is usually how we write a compound. Cation first, anion later. Okay, this is made by ionic compound, just like a sodium chloride, right? Sodium here, although we're writing the structure or formula as just a sodium and chloride. I didn't write the charge of there for the ion, but you need to think about this guy actually is made by sodium ion and the chloride ions. So this is how they form together. Okay, yeah. So or the magnesium chloride. Okay, magnesium chloride will have magnesium ions and the chloride ions over there. Okay, so we are going to form magnesium chloride over there. So cation first, anion later. Okay, cation first, anion later. Okay, yeah. So this is generally how we write the compound. And the major thing is the whole compound should be neutral, which means you need to make sure if we have if those two ions do not have the same charge, then you need to balance those two to make a correct formula based on the charge. Okay, make a correct formula based on the charge. For example, you see, magnesium has a 2 positive charge, and the chloride only have a 1 negative charge. And again, when those two combine together, should be a neutral, which means if you just have a one chloride combined with one magnesium, this is not neutral because this guy has a 2 positive, this guy is a one negative. They give us when those two combine together, we still have a 1 positive net charge, right? So that's why you need to have a 2 of the chlorine to balance the 1 of the 2 positive. So that's why you need to, when you write the correct formula, you need to base on the charge of the cation and anion to make a correct formulas. Okay, yeah. So this is give you one of the examples. Another example like aluminum. This is a very, very common. Aluminum has 3 positive charge, and we have chloride has 1 negative charge. So when we together, we should have 3 of the chloride ions to balance the 1 of the 3 positive charge, right? In this case, so that's why the aluminum chloride is writing like this. Okay, those are three is the script, is the subscript for chloride. Means we have three of the chloride ion. Okay, we have three chloride ion. This is a okay. So what else? For example, if we have aluminum and combine with sulfur, or let's say oxygen. Oxygen has a two negative charge. Okay, oxygen ion. This is oxide ion, and this is aluminum ion. How do we balance this? Okay, how do we balance this? And in general, the general way to help you to balance is you're just moving 2 over here, moving 3 over here. Then you will balance this. In this case, that means you're going to have a 2 shows over there. That means we're going to have a 2 aluminum ion. And a 3 goes under this. That means we're going to have a 3 oxide ion. You see, in this case, 2 aluminum ion has a 6 positive. 3 of the oxide ion has a 6 negative. 6 positive balanced with 6 negative, and overall is neutral. Okay, so when you write the formula, it's just aluminum, and then they say 2 go over there, so aluminum 2 and O3. So Al2O3. That's gonna be the formula for aluminum oxide. Okay, yeah. So this is generally how we write, but this is not always. For example, if we have a zinc 2 plus and the oxide 2 minus of there, well, if you're based on this rule, then you know the 2 should go over there, right? And this 2 also go over there. So when you write the formula should be zinc 2O2, right? Like this, right? But usually we're not writing like this. For ionic, I need to emphasize here, for only ionic, not for molecular compounds, but for ionic compounds, we need to keep the simplicity ratio. Keep the simplicity ratio. Okay, so this is 2 and 2. Keep the simplicity ratio should be a 1 and 1, right? So that's why you should write zinc oxide like this, not like this. Okay, yeah. So this is how we write those compounds formulas. Are you clear? Okay, so generally this is how we write the formulas. But the point is, okay, how can we? You may have a question. Okay, I know those elements, but how come I know those elements? What is the charge for each of the elements, right? For example, what is the charge for potassium? What is the charge for beryllium? So what is the natural charge for the chlorine? What is the natural charge for the oxygen, sulfur, or others? How can I know this? Right, that's confusing, right? Okay, yeah, yes, you don't know. I know it because I already do this for many years. Okay, yeah, so already familiar with that. Okay, so I will give you one of the sheet. It's called a common ion sheet. Okay, I'm going to grab it from my office. Just wait a minute. And again, the common ion sheet is the sheet that what? No idea why they print, I mean, 2 pages, supposedly we have just 1 page. Okay, so those are called the common ion sheet. And if you're looking at over here, they already have those common ions shows over there. Okay, yeah, doesn't matter. It's called a monoatomic cation. Monoatomic means one atom. Okay, and there's another one. It's called the polyatomic. Okay, polyatomic. That means we have a multiple atoms combined together, making an ion. Okay, we will talk about this later. Okay, so those are helping you to figure out the charge for each of this. But in general, sometimes you don't have to, especially when we talk about some A group, main group. You don't have to looking at the common ion sheet, you can still figure out the charge. Okay, for example, the metals. Usually in 1A group, in A group or main group, metal, we talk about metal always using metal usually is a cation, right? Has a positive charge. Metal's charge is equal to the number of group. Okay, so 1A group, those metals should has one charge, one positive charge, right? The metal, they always is a cation. The charge will be the number of the group. So 1A group, they are going to have a one positive charge, which means the lithium will have a one positive. If they become a charge, they are going to have a one positive charge, right? So lithium ion, this is lithium ion, sodium ion, potassium ion, and rubidium ion or Sicilian ions. Those are all positive charge. Okay, as long as it's in 1A group, they all should have one positive charge. Okay, and a 2A group, again, they should have a two positive charge because the metal's charge equal to the number of group and also should be a positive charge. So beryllium should have a two positive charge, and magnesium have a two positive, and the calcium has two positive, the strontium has two positive, barium has two positive. Okay, yeah, and 3A should also has a three positive charge. But 3A, very common, we commonly use is just aluminum, because you see boron here is a non-metal. Okay, this is you see the zigzag shows up there. The zigzag is the difference, is a boundary between metal and non-metal. The boron is a non-metal, but aluminum is a metal, and the rest of others is a metals. So aluminum should have a 3 positive charge. Gallium has a 3 positive. Indium has a 3 positive, and thallium has a 3 positive. Okay, so those are metals have 3 positive. Are you clear? Okay. And for those usually for those guys, sometimes their charge has a multiple charges. So we will talk about this later. But just to let you know, for those metals, usually those are 3 positive charge. And in most of the cases, iron has from 1 to 3 positive charges. Okay. Sometimes they have 4 positive charge, but not very often. Okay. So in general, those are numbers of the metal charge equal to the number of group. That's easy to remember, right? Okay. And for the non-metals, the charge is equal to the group number subtract the equal to the group number subtract the that's equal to the group number subtract the 8. Subtract 8. 8 is a magic number in chemistry. Okay, a lot of cases we talk about 8. For example, okay, if we have a 6A group, 6A group, that's a oxygen, sulfur, and that is selenium and toluene. So for this guy, their charge, again, the non-metal usually is anion. So their charge equal to 6 minus 8. So that's why they have a 2 negative, 2 negative, 2 negative, and 2 negative. Okay, yeah, so this is how we count this. 7A group, then that's fluorine, chlorine, bromine, and iodine. This guy has a 1 negative charge because this is a 7 minus 8, so 1 negative charge. And generally, this is how we combine and calculate, figure out the charge. So as long as we know the charge for each of the ions, we know the cation's charge, we know the anion's charge, and we combine them together based on the to balance the charge for the cation and the anion and make a neutral, and then we generally can write all kind of the formulas for the ion compound. Make sense, right? Yeah. All right. So we're done for today. Okay, and let's move to the lab.